Good morning. Welcome one and all to the session on computer organization and architecture. We started with Unit 1 when we've had the description of a basic computer design. We have looked into the difference between computer architecture and organization. Architecture is the abstract model of the computer that you design. So it's only a design view of the computer. We've seen that computer architecture is of two types. The first one is a von Neumann architecture and the second one is a Harvard architecture. In the von Neumann architecture, we have the CPU made up of ALU and the control unit, to which IO processor is connected, and through the IO processor the IO devices can interact with the CPU. And we also have a memory that is connected to the CPU for storing both instruction and data together. This is called as the von Neumann architecture, and our entire curriculum is going to be on von Neumann architecture. The second type of architecture is the Harvard architecture, where different memory units are used to store data and instruction. So the memory that is used to store instruction will store only instruction, and it is not capable of storing data. So this is the Harvard architecture. This is used only in certain mainframes and certain biomedical systems, and which is not of concern to our curriculum. So all the PCs, laptops that we use only the von Neumann architecture. So we'll be learning anything that is in your curriculum is going to be on von Neumann architecture. Now we have seen that the instruction and the data operands are stored in the same memory, and our instruction format is going to be of 16 bits and our data is going to be of 16 bits, because our memory was designed with a 16-bit word. So there are 4096 such words or locations in memory, each capable of storing 16 bits. And we have also seen what is computer organization. It is the realization or implementation of the basic design into hardware. And we have seen some of the registers used in the computer. Registers are named memory locations which are hardwired to the CPU. So unlike a separate memory unit, you have certain memory slots alone available directly on the CPU, which are fabricated on the board. So such memory locations are called as registers. And we have seen that for the basic computer that we are trying to design here, all the data and instruction registers will be of 16 bits and all the address registers will be of 12 bits. So this is the design that we have seen earlier. We have a memory with 4096 words, 16 bits per word, and any data or instruction you draw from this memory is going to be of 16 bits. So the instruction register, the temporary register, the data register DR, and the accumulator AC, all of them have 16 bits. When we try to address this 4096 words, we are going to need 12 bits to indicate each location uniquely. So the address of every word in this memory is going to be 12 bits. So any register that is used for storing addresses are also going to be of 12 bits, which means the program counter and the address register, the program counter PC and the address register AR are going to be 12 bits each. And our input and output registers, which we are trying to use for getting data or giving data to an input output device, is through the input output register, each of 8 bits long. And we have seen how many bits and what the functions of these registers are. Once you know this, we have moved on into 3 different types of instructions, and we have seen how the instruction formats are going to be for these 3 instruction formats. Now the first instruction is called as the memory reference instruction. Anytime you try to access memory or read something from it or write something to it, it is called as a memory reference instruction, for which the format will have uh, the first bit or the most significant bit is used for indicating the addressing mode, and followed by 3 bits for opcode, and bits 0 to 11 are for giving the specifying the address. The address is the location of the data where they can find in the memory. So every time we try to access memory, we are going to give some address value, and from that address value we will locate the data. And this addressing mode I is used to indicate whether it is a direct addressing mode or an indirect addressing mode. Its value is 0 for direct addressing mode and its value is 1 for indirect addressing mode. And we have also seen how what's the difference between direct and indirect addressing mode. In direct addressing mode, the address value which is given in the instruction specifies the location in memory where the operand can be found. Whereas in indirect addressing mode, the address given in the instruction links to a location in memory where the exact location of the data can be found. So you can see the difference in these images. And then we moved on into register reference instruction, where the first 4 bits are fixed for register reference instruction. So it's going to be 0 1 1 1 for any register reference instruction. So this is how they differentiate between a memory reference and a register reference instruction. And because we are not trying to access memory in register reference instruction, the bits 0 to 11 need not store any address value, so they can be used to indicate what operation a register has to perform. So that operation code is specified in 0 to 11 bits in the register reference instruction. And then we have the input output instruction. In the input output instruction, all the first 4 bits are fixed as 1, which means the MSB 15 along with the bits 14 to 12 are all fixed to 1. So the first 4 bits are always going to be 1 1 1 1 for any input output instruction. And the operation to be performed is specified in bits 0 to 11, because these bits are not required to specify any address from the memory. They are used to specify the operation to be performed. So these three are the instruction formats we have seen. Now we have to design a hardware circuit that can help us execute these instructions. The next thing we will talk about is the timing and control. So when I try to execute some instruction, there are two things that are primarily important in a computer. One is maintaining timing between different parts of the computer, and the second one is control of all these parts. So for the timing aspect, we are going to use a master clock generator. This clock generator is just a pulse. So this pulse is applied to all hardware circuits that are inside the computer. So what is a clock signal? The clock signal is something that is used for sending a timing information to all parts of the computer. All parts of the computer will work on the same timing. So if I say send this data to a memory unit, the next clock cycle it should be able to send me the reply. Likewise, so it's a periodic signal. So this signal is being transmitted throughout the computer. So that is called as the master clock. And for control, we need to have certain other signals that can help us direct the different parts of the computer. When the instruction says read some data from memory, the memory should receive a signal to send that data out of it, and there should be some register which can receive that memory or read that data from the memory. So a register needs a signal and the memory device also needs a signal. These signals are called as control signals. So every time there has to be some operation that's to be performed, some control signal along with the timing signal is given to different parts of the computer. Such signals are called as control signals. These control signals are given to registers or other circuits or memory devices or input output devices depending on the instruction that we receive. So I should look, the control unit should look into the instruction and it should start issuing control signals. So the main work of the control unit is to generate these control signals. So the control unit has to generate these control signals based on the input instruction that we have given. Now, when we are trying to control, who will receive these control signals? These registers and memory, they have to respond to the control signal along with the timing signal. So when I say read some data from memory into the accumulator, the memory should receive the control signal and the timing signal. The accumulator register should receive the control signal and the timing signal. Depending on when the control signal is issued, accordingly, that particular following timing signal, the register will respond or the memory device will respond. So I need to identify at what point of timing signal I have to issue the respective control signal. So these control signals are generated and they are shared through a common bus mechanism. We will look into how this common bus mechanism works. So a common bus is a wire that connects all of the parts of the computer, and these signals are transmitted on that particular wire, and that wire reaches to all parts of the computer, and when these parts receive that input, they respond accordingly. The difference between a wire and a bus is that a wire carries only one signal, but a bus is capable of carrying multiple signals parallelly. So I can send, it's like a bifurcated wire. So in the bifurcated wire, one line can carry the timing signal, the other line can carry the control signals, which is why it's called as a bus. And this bus is used for connecting with all the paths. All the timing and the control signals are transmitted through the bus. Now, depending on how these control signals are generated, there are two types of control units. The first one is called as a hardwired control unit, and the second one is called as a microprogrammed control unit. In a hardwired control unit, the control signals are generated using a hardware circuit. So the instruction register which receives the instruction to be executed is connected to a separate hardware, and that hardware generates certain signals by decoding that instruction register, and then it gives that decoded it generates the control signal and it sends to all the other parts of the computer based on through the common bus and along with the other timing signal. That is called as the hardwired control unit. In a hardwired control unit, the entire design is fabricated on the board. So I design a hardware circuit, and the hardware circuit is fabricated as part of the integrated chip. So you integrate it on the board and then fabricate and give that board. That's called as a hardwired control unit. The disadvantage of having a hardwired control unit is that after I have decided on the instruction, I design the circuit and the circuit is fabricated. If I want to add any new instruction to the computer, I cannot do so, because if I have to do that, I have to redesign the entire hardware, I have to fabricate the entire hardware again and then produce that machine. So the instruction or the programs that can be written are very, very less, or the choice of instructions becomes very less in the case of a hardwired control unit. Whereas the microprogrammed control unit is a little different. The microprogrammed control unit is more like a operating system. So what I say is, whatever instruction I give to the computer, it is stored in the instruction register, and the instruction register is decoded by another program. Or for every instruction, say for example, the instruction gives add A and B. or add the contents of accumulator and the data register is the instruction. In that case, it goes and looks up inside the memory. The memory will have some piece of code which says at timing signal T1, you take the input from accumulator. At timing signal T2 or the second clock cycle, you read the data from the data register. At the next clock cycle, you add both of them and put it inside the accumulator. Likewise, the sequence in which the operations are done are written as micro operations or as a micro program in the memory. And every time the control unit wants to do something, it will ask the memory unit to tell what it has to do. It will say, I have got an instruction, add A and B. It will go and tell the memory unit. The memory unit will search itself and find out what to do with that instruction, and it will give what are the timing signals to be generated. So once that it gives back the list of control signals and timing signals to be generated, the control unit will accordingly generate those signals. This is called as a micro-programmed control unit. So these two are the two major types of control units. When we look into your curriculum, we have got a hardwire control unit which is in unit 1. So this includes the design of a hardware circuit that can act as a hardwired control unit. So that is what we call as basic computer organization and design, under which we have the timing and control instruction cycle and this complete computer description. All of these deal with the hardwired control unit. The first unit later bit also includes a micro-programmed control unit. For now, I will not be touching on the micro-programmed control because it's completely a different aspect. It needs a different perspective. So we will look into the hardware design and directly move on into unit 2 for now. And then we will understand how this hardwire micro-programmed control can also work. So in a hardwired control unit, we have to design a hardware circuit that can generate control signals. The only inputs the unit has are the clock signal for the timing and the instruction which the user gives. So based on the instruction only, we have to do some processing. So based on the instruction, we have to generate some control signal. So for generating of control signals, the two major inputs the hardware design has to have is the clock signal and the control signal and the instruction. Now if we look into the instruction register has actually three parts. The bit 15 has the addressing mode bit I, and bits 14 to 12 has the opcode, and bits 0 to 11 have the address in the case of a memory reference instruction. In other instructions, bit 15 to 12 are set to certain specific value, and bits 0 to 11 are used to indicate the operation to be performed. So we are going to design our circuit based on only these two aspects, the clock signal and the instruction. Now we will see what a clock signal is. This is how a clock signal looks like. It is nothing but a square pulse or a digital pulse. The high end can be a 5 volts and the low end can be a 0 volt. So it is only a voltage that is sent as a clock signal. So for a certain period of time, a high wave of 5 volts is sent, and then for a certain period of time, a low of 0 is sent. So this is how a clock pulse is. The width of the clock is the raising and the lowering of a clock pulse. So the time it raises to high and the time it falls to back to 0 is called as the width of the clock pulse. And one upper cycle with one lower cycle is called as the clock period. So when I say clock cycle, it includes one upper wave and one lower wave. So that is called as the clock cycle. And the after the clock cycle, so if whatever you see here as the first clock period is one cycle, any instruction that has to be executed, it should be done in one clock cycle. So when I give an instruction to the computer, it will take n number of clock cycles to complete execution of the instruction. It depends on what type of instruction we have. Certain instructions use multiple clock cycles. Certain instructions use only one clock cycle. So it depends on the type of instruction we have. But the number of clock cycles is going to be fixed for a particular instruction. Say for example, if I say add a comma b, it will take only n number of clock cycles. If I say write into memory, it will take only x number of clock cycles. How many ever times I repeat the instruction, it will take the same number of clock cycles every time for execution. Now, this clock cycle is given as an input to all the registers. So we have seen this is our basic design which we designed earlier. So we have got some registers here. All of these registers receive a clock cycle. The data register and the accumulator register also will receive the clock cycle. The clock cycle is represented using a triangular arrow which is put inside of the register. So this symbol indicates a clock cycle. The one that you see here indicates a clock cycle. Do you see the arrow there? That is called as the that's an indication of the clock cycle. So this clock cycle is one input which is given to all the registers and the memory. And we are going to design a hardware circuit that can take both the clock pulse, and I need to generate some control signal based on the instruction register. So this is what I have. Now I have to have some control logic gates. Imagine this structure is a control logic gate. I need to prepare that circuit, and that circuit will give me control outputs, or it will generate some control signals. To do that, the only inputs that I have are instruction register and the clock cycle. Below you can see that there is a clock cycle. We will decide what to do with the clear and the increment also. I'll tell you what they mean. So this only input that we have are instruction register and the clock input. Based on this, I have to design a circuit that can generate control signals. Now when I look into the instruction register, we have 3 bits of instruction, which is bit 14 to bit 12. These 3 bits can take 8 different values, or these 3 bits can indicate 8 different operations to be performed. So it can be 000, 001, 010, 011, 100, 101, 110 and 111. These 8 are the values that can be given in the 3 bits. I need to generate 8 different signals out of these 3 bits. So what circuit should I use for indicating these 8 operations differently and uniquely? So for that, I am going to use a decoder circuit. So it takes a 3x8 decoder. It takes all the 3 values as input, the 3 bits as input, and it generates control signals, or 8 different signals, D0 to D7. Clear? Are we clear till here? So we are trying to generate some signals from the instruction register. So once these D0 to D7 are generated, I give it as the part of the control input. Now, for in the case of a memory reference instruction, all the 11 bits which are in 0 to 11 area of the instruction register will directly be used for the decoding of the will be directly used as a memory address. So in that case, I can directly give all the 11 bits into the control input. And in the case of a memory reference instruction, we also see that bit 15 is used for the addressing mode, right? Now, when we look into the addressing mode, I need to place the address and I need to access some data. For accessing, we are going to use the common bus system. Imagine this is the bus system. All the units are connected to the common gray color wire that is shown around is called as the common bus. This common bus uses some signals to identify each unit. Okay, for memory unit, it is mentioned that number 7, and for the address register the value 1 is mentioned. So depending on some value, that particular unit will be activated. So it is this control signal is used for activating specific registers in the control system. So if 7 is passed on to the in the bus, memory unit will receive that control signal, and when memory unit is activated, whatever data it has got, it will put inside the bus. And whatever data is inside the bus, the accumulator will take in if the load signal is sent high. So this is a basic model in which different parts of the computer interact with each other. So when I say the accumulator has to read, one control signal to the accumulator is made high and the corresponding accumulator is activated in the bus circuit. So whatever is in the bus will be pushed inside the accumulator. So that's how it works. Now with that idea, so we are going to use the same idea for generating these control signals also. Now I need to tell which device has to be activated. Having that in mind, if the bit 15 is 1 or 0, it can either be direct addressing or indirect addressing. So that is also given as a control input. So the control inputs, as far as we have seen now, are the 8 control signals generated from the 3 bits of the instruction code, which is D0 to D7, and then we have all the 11 bits of the instruction register are given as inputs, and the addressing mode bit I is also given as input. Okay, now when I say read data from memory, it doesn't happen in one clock cycle. So imagine I have multiple clock cycles. I have a clock cycle 1, clock cycle 2, clock cycle 3 and clock cycle 4. In the case of a read operation, the first signal is sent to the address register and I need to specify from which address I have to read the data. So a control signal is given to address register, and when the load signal is raised high for the address register, the address register will take whatever data is available on the common bus. I have placed the 0 to 11 bits of the instruction register on the common bus. So when the load signal is raised at clock cycle 1, the address register receives the address which is traveling in the bus. This happens in clock cycle 1. The second clock cycle, I need to tell memory to read the data from that particular address. So what I do is I give access to the memory unit and I say I increase the read signal of memory unit. When I raise the read signal of the memory unit, the address from the address register is received by the memory unit, and that particular data is thrown inside the common bus. So that happens in the clock cycle 2. So in clock cycle 2, the data from memory unit is put inside the common bus. And in clock cycle 3, the data which is in the common bus has to be received by the accumulator. In that case, the load signal of the accumulator is raised high during the third clock cycle, and it receives whatever data is there in the bus structure. So this way, the different signals are generated at different clock cycles, and any instruction can have any number of clock cycles. So for a read instruction, which example I told, we needed 3 clock cycles for reading some data from memory. While writing into memory, we may need 4 clock cycles. While trying to read an input from an input device, we may require 8 clock cycles. So it depends on the type of instruction that we are trying to execute. So based on that, for the basic computer structure, it has been observed and finalized that no instruction needs more than 16 clock cycles. So the maximum number of clock cycles any instruction used for this basic computer or this instruction set does not need more than 16 clock cycles. So in that case, we are going to generate some timing signals from timing signal T0 to T16. So this timing signal is going to be generated for using the clock cycle, but I am going to generate 16 different timing cycles from the clock that is generated. So these timing signals depend on the instruction, and they also indicate what portion of the instruction we are executing. Now, like for example, when we tried to execute the read instruction, we saw 3 different operations to be performed. One is loading of the address register, the second is releasing of data from memory, and then the third one is reading of that data into the accumulator. So we have 3 operations which are called as micro operations. For every instruction, you can convert them into multiple micro operations and perform them on different time cycles, T0 to T15. So you have maximum of 16 time cycles. So this timing cycle can be generated from a decoder. To generate 16 different outputs from a decoder, we need 4 inputs minimum. So my circuit is going to have a 4x16 decoder, which is capable of generating 15 timing cycles, 16 timing cycles, T0 to T15. And to give as input to these 4x16 decoder, I have certain inputs. I can either use a clock or an increment or a clear signal. This clear signal is used for indicating completion of a particular instruction. So imagine I have generated time cycle T0 and I tried to load the address register in the case of a read instruction. So the read instruction adds the address into the address register at time cycle T0. At time cycle T1, the memory releases the data into the bus. That happens at time cycle T1. And at time cycle T2, the data is absorbed by the accumulator from the bus. So I have completed my instruction execution within 3 clock cycles, and at time cycle T2, my instruction execution is complete. So the next time cycle, I have to start afresh and start executing my next instruction. For that, I am going to use the clear input to state that the instruction is complete and I have to start generating from cycle T0. For that, I am going to use an input called clear. These are used and then Another decoder is used for this purpose, which takes input from clock, clear, and increment, and it generates 4 bits. These 4 bits are called as the sequence counter bits. We will see what the sequence counter is when we try to work with some of the instructions. So for now you understand a sequence counter is used to generate 4 bits from the clock, clear, and increment inputs, and this 4 are given to a decoder to generate the different timing signals. So we have control signals that are generated from the input instruction register and some timing signals generated from the clock input. All of this are given into another hardware, and this hardware is called as the control logic gates. It is responsible for generating the control signals. So this is how a hardwired control unit is designed. So with this, I will stop for today's session. We will look into how exactly this control logic gate system is designed in the next few sessions. So with this, I will stop here. Thank you one and all. I hope all of you are good. Stay home, stay safe. See you all soon. Thank you.